Hello, welcome back to another episode of Math with Haas. Today you are watching Precalculus Season 1, Episode 10. So we are continuing our exploration of exponentials and logarithms. In the previous episode we looked at solving exponential equations. Now we will look at solving logarithm equations. So let's consider the following example. We have 4 plus 3 log of 2x is equal to 16. Now, the basic principles of solving our logarithms will be the same as with exponentials. So let's get our basic principles. Our first principle is going to be isolating the log. So, in this case, we notice we have a 4 plus 3 times log of quantity 2x is equal to 16. What we need to do in order to isolate the log is we'll have to get rid of this 4 and then this 3 coefficient. So I'm going to subtract the 4 and have 3 log of 2x is equal to 12. Now, there are two ways I can go about with dealing with this coefficient. One would be using this law of logs, where we know that c times log of a is equal to log of a to the c. Now, this way here would make our problem a little more complicated later on, precisely because we would have a quantity of 2x that is raised to the third power, when what we can do right now is just simply divide out to 3. So while we could use our law of logs and solve it later on using that, it will be a little more complicated route to go, especially when we have this easier route of just simply dividing by 3. So now we have log of 2x is equal to 4. Now, we have completed our first step, and that is isolating a log. So the next step is exponentiate. So when we had an exponential, we would log it to undo the exponential and get access to what was inside of it. In this case, what we're going to do is exponentiate to undo the log. So we're going to use this basic idea from our properties of logs, where we had a to the log base a of x was equal to x. And we could think of the exponential and the logarithm as canceling each other out, since they are the inverse functions of each other. So when I look at this log, I notice that there is no base written here, which means this is the common logarithm, which is log base 10. So I am going to take both sides of our equation, and they will become the exponents of our exponentials with base 10. So we'll have 10 to the log of 2x is equal to 10 to the 4th. This is what exponentiating looks like. We took what we previously had and we took an exponential and raised it to that power. So when I look at the left side now, we can apply our property, which we restated over here, and the log and the exponential kill each other off, leaving us with 2x is equal to 10 to the 4th, which is just 10,000. Now we can divide both sides by 2 and get x is equal to 5,000. So this is our first example to get our feet wet in this subject. Let's consider a more tricky one. So for this example, suppose we had log of x plus 2 plus log of x minus 1 is equal to 1. Now in this case, we have a log plus a log. And so in one sense, the logs are already isolated because there's nothing but logs on the left side, but on the other hand, there's two log expressions. How we want to deal with this is the clue that we have a log plus a log. And that means we can use our law of logs. If we have log of A plus log of B, this we said was equal to log of A times B. So we can do that. So the left side will become log of the quantities x plus 2 multiplied by the quantity of x minus 1. All that's inside the log, and this is equal to 1. We have now isolated the log, and now we need to exponentiate. And now that I look at this, I realize I forgot our third step up here, which was simply solve for x. Alright, so let's add that, and we'll come back to here. So, looking at this, again we have the common logarithm, so I'm going to exponentiate with log base 10, or with the exponential base 10. So we have 10 to the log of the quantity x plus 2 times the quantity x minus 1 is equal to 10 to the first, which is just 10. Now again on the left side, the log and the exponential, since they are the same base, they will smote each other upon the mountainside. They kill each other off, leaving you with just x plus 2 times the x minus 1. So we have x plus 2 times x minus 1 is equal to 10. Now this is now a nice quadratic equation, and we need to get the left, or we need to get one side to equal 0. So I'm going to subtract the 10 over, and our next step, oops, I forgot my minus 10. Let's move that over. Minus 10 is equal to 0. So looking at this now, in order to figure out what x is, we're going to have to distribute, or what a lot of you have learned as FOIL. We could think of it as doing a double distribution. So when we distribute this, we have x squared plus 2x minus x minus 2 minus 10 is equal to 0. So x squared plus x minus 12 is equal to 0. We can now factor this as x plus 4, x minus 3 is equal to 0. So x will equal negative 4 comma 3. Alright, that is our answers. So in this case, we had it started out as a log plus a log, but it turned out that we had really a log with a quadratic inside, which is why we got our two answers here. Alright, now let's see if we can find a more interesting example. Here we go. The natural log of x plus 2 plus natural log of x plus 1 is equal to the natural log of 4x plus 14. Now in this case, the principles are the same. We have a log plus a log, so we can use the same law of logs. And so we have natural log of the quantities x plus 2 times the quantity of x plus 1 equaling the natural log of 4x plus 14. Now at this point, we could take one of these logarithms, either the one on the left or right, and subtract it from both sides. So all the logs are on one side. However, that will create quite a mess for us later on when we want to solve this, because we would have a log minus a log, which then we would need to use the law of logs for subtraction. So, for example, we'll just do this off to the side. How about green? So we would have natural log of x plus 2 times x plus 1. All this would be subtracted from natural log of 4x plus 14. This is equal to 0. We could use our law of logs here, where you have log of a minus log of b is equal to log of a over b. So then we would have this expression here inside a log, all of which would be equal to 0. This would take a little while to untangle, but it's doable. An easier way, instead of going this route in green, is noticing that we have a log on both sides that is of the same base here. So I'm going to just exponentiate. So we should probably move this green out of the way. So I'm going to exponentiate. The natural log here, for you remember, is log base Euler's number. So our exponential is going to be e. So e to the natural log of the quantities x plus 2 times x plus 1 is equal to e to the natural log of 4x plus 14. Now on both sides we are applying our same property, so we get our mutual slaughter on both sides there, leaving us with x plus 2 times quantity of x plus 1 is equal to 4x plus 14. Who knew mathematics could be so violent? Now, at this point, we need to do our distributions again. So we'll go ahead and do our distributing. That gives us x squared plus x plus 2x plus 2 is equal to 4x plus 14. And we can start combining terms. We have again a quadratic equation. I can see that right away because we have this squared term here, which means we're going to want to subtract this 4x plus 14. So let's move all that over. So that leaves us with x squared minus x minus 12 is equal to 0. This looks suspiciously familiar with our previous example. And so we get x minus 4, x plus 3 is equal to 0, or x will equal negative 3 comma 4. Alright. So we have now looked at how to solve logarithmic equations. What is next is applications of exponentials and logarithms and how they're used to model real-life phenomenon that in the world. We'll have a variety of examples. We've already seen some applications with population, radioactive decay in the early episodes. What we're gonna, and can't forget about compound interest, of course, but in our next few episodes, 2, 3, we will be hammering in more detail on some of these different applications. There are all sorts of interesting applications we'll look at, such as the decibel scale, how earthquake intensities are measured, their magnitudes. We'll look at Newton's cooling formula. So lots and lots of interesting details. So thank you for watching another episode of Math with Haas. If you have been enjoying our content, please subscribe and support us on Patreon. Thank you for watching and for joining this math party, and I will see you next time.